James Webb and the mysterious weather of a starless world. James Webb Space Telescope has observed something that challenges our usual idea of what a planet needs to remain active. Around 20 light-years away, the object SIMP 0136 appears to be drifting through space without orbiting a star. Yet when Webb observed it in infrared light, its brightness changed as the object rotated. There was no sunrise and no sunset. No nearby star was illuminating its clouds. Instead, the object produced its own infrared glow through the heat and activity within its atmosphere. SIMP 0136 is roughly 13 times more massive than Jupiter and rotates incredibly quickly, completing one rotation in about 2.4 hours. That rapid rotation gave Webb a rare opportunity. Rather than observing the object at just one moment, scientists could watch different regions of its atmosphere move into and out of view. The changes were subtle but extremely important. Different infrared wavelengths became brighter or dimmer as the object rotated. Those variations provided clues about different layers of its atmosphere. Scientists are not looking at continents, oceans, or a visible surface. Webb is measuring infrared radiation and analyzing the patterns hidden within that light. From those measurements, researchers can work backward to understand temperature differences, clouds, chemical composition, and other atmospheric processes. Some of the observed signals appear to be associated with different atmospheric layers. Deeper regions may contain clouds involving iron particles, while higher layers could contain silicate minerals. There are also indications of hotter and colder regions within the atmosphere. This is nothing like ordinary weather on Earth. Our clouds are primarily made from water. On a world this massive and hot, atmospheric conditions can be extreme enough for materials such as metals and minerals to participate in cloud formation. The fascinating part is that these atmospheric features change as the object rotates. A region can move toward our line of sight and make one wavelength brighter, while another atmospheric layer produces a different response. That means Webb is effectively studying weather on a world that has no conventional day or night. But there is an important scientific limitation. A change in infrared brightness does not automatically tell researchers exactly what caused it. A brighter region could result from higher temperatures, thinner clouds, or deeper layers becoming visible. A darker region could be caused by thicker clouds, cooler temperatures, or atmospheric chemicals absorbing radiation. Several processes may be happening at the same time. This is why observations like these are so valuable. Webb is not simply taking photographs. It is collecting detailed spectra that allow scientists to separate different atmospheric signals. During observations of SIMP 0136, Webb's instruments collected thousands of spectra while the object rotated. The rapid measurements allowed researchers to construct detailed light curves and compare changes across different infrared wavelengths. In effect, a distant point of light becomes a rotating atmospheric laboratory. And SIMP 0136 is not the only isolated object creating questions. Webb has also studied another isolated brown dwarf, W1935, where scientists detected unexpected methane emission. Because the object does not have an obvious nearby star providing stellar wind, researchers have considered several possible explanations, including auroral processes and other sources of energy in the upper atmosphere. That possibility is particularly interesting. Auroras on Earth are associated with energetic particles interacting with our magnetic environment. Other planets in our solar system also produce powerful auroral emissions. But an isolated object without a host star presents a different puzzle. Where does the energy come from? Possible explanations include internal atmospheric processes, interactions with surrounding plasma, magnetic activity, or other mechanisms that scientists are still investigating. None of this means Webb has discovered artificial lights or extraterrestrial technology. The glow is natural. And that is scientifically more interesting. It suggests that a world does not necessarily need a nearby star to remain physically active. Internal heat, atmospheric chemistry, magnetic fields, and other processes can continue producing observable activity even in complete interstellar darkness. The dark world's web is teaching us to see, but SIMP 0136 may only be the beginning. The most important question now is not what makes one isolated world glow. It is how many other worlds could be hiding in the darkness between the stars. Astronomers have already found evidence that free-floating planetary mass objects exist. But detecting them is extremely difficult. Unlike ordinary exoplanets, these worlds do not regularly pass in front of a bright star, and they do not necessarily produce an obvious gravitational signal that can be easily measured. Their greatest clue may simply be their own heat. That is where infrared astronomy becomes incredibly powerful. Visible light tells us what objects reflect or emit in wavelengths our eyes can detect. Infrared light can reveal thermal energy and chemical signatures that remain completely invisible to human vision. For a young, massive, isolated world, that heat can make the object detectable even though there is no star nearby. But as such an object ages, it gradually loses its stored heat. Its infrared signal becomes weaker. Eventually, an older free-floating world could become incredibly difficult to find. That means the galaxy could contain many more rogue worlds than current observations reveal. Some might be relatively warm and bright in infrared. Others could be ancient, cold, and almost completely hidden. And there is another fascinating possibility. A free-floating planet does not necessarily have to be completely alone. If a giant planet was ejected from its original planetary system, some of its moons could potentially remain gravitationally associated with it. Whether such systems can survive their violent history depends on many factors, but the possibility creates an entirely different kind of planetary environment. Imagine a giant world moving through interstellar darkness with a moon orbiting around it. There would be no normal sunrise. But the moon could still experience gravitational interactions with its parent planet. If the system contains strong magnetic fields, energetic particles could potentially create unusual atmospheric effects. From a distance, Webb might not directly see every part of that system. Instead, it could detect an unusual chemical signature or changing infrared emission. That would not automatically prove the existence of a moon. Scientists would need multiple observations and competing explanations would have to be tested. This is an important distinction. Astronomy often begins with something strange and ends with a much more complicated explanation. A mysterious emission might initially appear impossible, but eventually researchers may discover that ordinary physics operating under extreme conditions can produce it. That is exactly why objects like SIMP 0136 and W1935 are so valuable. They allow scientists to test their models. They provide real atmospheric data from environments that cannot be recreated easily on Earth. And they help researchers understand what natural processes can produce unusual signals. This becomes especially important when astronomers begin studying smaller planets. Suppose a future telescope detects a faint infrared signal from a distant world. How will scientists know whether that signal comes from clouds, temperature variations, atmospheric chemistry, magnetic activity, or something else? The answer will come from studying many different worlds and learning their patterns. SIMP 0136 becomes one piece of that enormous puzzle. Its rapid rotation allows astronomers to watch its atmosphere change on timescales of only a few hours. That is extremely useful. If a particular infrared feature repeatedly appears and disappears with the object's rotation, scientists can investigate where in the atmosphere it originates. Different wavelengths can then be compared. One might reveal deeper clouds. Another could probe a higher layer. Another could reveal temperature changes. Together, these signals create something resembling a three-dimensional atmospheric map. And those changes can travel across space as faint infrared signals until they finally reach a telescope millions upon millions of kilometers away. The object may remain forever beyond human reach. But its light can cross the darkness. And through that light, astronomers can begin reconstructing an entire world. That may be the future of planetary science. Not simply discovering where worlds are, but learning what is happening on worlds we can never visit. And somewhere in the darkness between the stars, there may be countless more waiting to be found.